So our second user paper today is on advancements in AI for low power verification. We have two speakers, Ramya from the KS Rangasamy College of Technology, where she is assistant professor, and Dr. Sivanandam from the Kumaramasi College of Engineering, where he is associate professor. Ms. Ramya is as I mentioned, is an assistant professor. She holds a BE in electronics and communication engineering and a master's in applied electronics. She researches into image processing, machine learning, deep learning, and IoT. Dr. Sivanandam is an associate professor. He has 15 years of academic training and teaching experience. His research areas include low-power VLSI design and verification, VLSI signal processing, and VLSI for telecommunication. Okay, over to you, please. Thank you.
Thank you, sir, for the kind introductions. Today, my presentation topic is advancements in AI for low power design and verifications. Nowadays, AI plays a vital role across all the fields. The development of AI is transforming low power design and verifications, improving power management and reducing the design cycle to meet the increasing demand in today's tech-driven world for energy efficient electronic devices. As the complexity of semiconductor design increases, advanced AI techniques are transforming low power verification in semiconductor design, thereby improving the energy efficiency and reliability of ICs. The next one, AI-driven power modeling. It improves energy consumption and system performance by predicting power, scaling voltage, and enhancing design space exploration in electronic systems. The AI models can accurately predict dynamic power consumption by analyzing RTL design, activity, and some more features. The machine learning can enable real-time voltage adjustment, ensuring performance outputs are maintained while optimizing power consumption. Here, AI enables fast evaluation of various low power design alternatives to find the most efficient implementations. Then machine learning powered verification. Here the three parts. First one is the intelligent test bench. Here the AI algorithms maybe now create customized test benches, enhancing efficiency and accuracy in low power functionality verification in designs through precise and automated testing. The second one is automated defect. Here, AI-driven diagnostic tools enhance efficiency by utilizing machine learning algorithms like supervised machine learning and unsupervised machine learning to identify power-related problems and reduce outage and optimize energy consumption in the real time. The third one is the anomaly reductions. Here, the power system defect can be identified early in the design process by machine learning tools, which enables proactive modifications, thereby resulting in more reliable and efficient power systems. Here, the efficient hardware accelerators. Here, the neural network used in the low power verifications. The specialized AI accelerators optimize neural network interference of energy constrained peripheral devices and enabling high efficiency system on chip architectures. The integration of AI with low power design, along with the emerging technologies like ReRAM, that is resistive random access memory, then drives ultra low power, then high performance AI processing. The next one's the reinforcement learning. It is used for the power optimization. This one type of machine learning. Here, in order to optimize energy efficiency, reinforcement learning, agents have the ability to adjust the system level power factors in real time. The oral algorithm smart schedule duties on heterogeneous hardware, thereby reducing the overall power consumption in the electronic devices. Oral modules continuously system behavior by balancing power and performance. Here, the bridging the schematic gap is power-ended extraction. The AI techniques optimize power management by converting high-level power requirements into reliable design constraint, thereby improving system performance and achieving the energy targets. The second, hierarchical power modeling. AI power models support exact optimization by bridging the distance between system and gate level power analysis. The third one is the automated low power IP generation. The AI generate IP modules that are highly optimized and power efficient to improve performance by utilizing high level specifications. Here the reliable and trustworthy AI. Here the explainable AI is models provide the designers with good understanding of power optimization decisions. It is allowing them to make smart and efficient design decisions that achieve power efficiency without reducing the performance. The next AI system must be robust to must attack that comprehends to low power operations in order to ensure the safety and reliability of AI powered low power solutions. It is important to perform through testing and validation process, which protect both performance as well as the security. Is the part here the three emerging areas concerned. One is the quantum computing. The second area is neuromorphic hardware. The last one is the mixed signal AI. Here we will face some key challenges. The scaling AI models and trusted AI deployment process. The third one is the bridging abstraction levels. So the current research direction is based on the extreme energy efficiency and adaptive self-optimizing systems, then AI-driven design automations. The current future directions in the low power verification based on the AI technology. Next one, AI and machine learning for low power verifications. Here, by providing more efficient and accurate methods for evaluating energy efficiency and power consumptions. Advancements in AI and machine learning are transforming low power verifications. These technologies allows researchers to optimize the verification process, then providing that electronic system satisfy exacting power specification while maintaining the functionalities of the device. Next, predictive power modeling. Here consider power estimation, then dynamic adaptation, then design space exploration. Here the dynamic power estimation, the AI-based models assist yearly optimization verification by enabling reliable prediction of hardware power consumption. It is only based on the hardware devices. The real-time power monitoring and dynamic adjustment of system, the factors to reduce the energy consumption may be assessed by machine learning techniques, either supervised or unsupervised, then reinforcement learning. It is based on our applications. Furthermore, the identification of optimal power performance trade-off early in the development process becomes easier by driven design space exploration. The next one, anomaly detection for verifications. The anomaly detection low power verification helps identify power consumption irregularities, ensuring designs meet energy efficiency standards. It's preventing power-related issues and optimizing electronic system reliability. Here, the machine learning algorithms improve the early detection of design defect by the identifying the unexpected power consumption in the patterns. AI power tools streamline the verification process of quickly diagnosing the root causes of power-related problems in our circuit levels. ML-based test generation optimizes verification coverage by focusing on critical power-related scenarios. Next one, energy optimization strategy. Here we consider the three factors, the hardware part, then software optimization, then AI-driven optimization. The first hardware techniques, the reduction of energy consumption is based on the implementation of voltage scaling, clock gating, and power-aware design methodologies. The second software-based, the energy efficiency is significantly improved by compiler and the runtime optimization, as well as the meticulous selection of the ML algorithms. The last, furthermore, energy efficiency is further enhanced by machine learning-based techniques for task scheduling, resource allocation, and power management. Now I will hand it over to Dr. Sivanandam, who will continue with the presentation.
Thank you, Ramya. So, in continuation with this design and verification, so now I'm going to start with simulation-based verification. Next slide, please. So, in present scenario, so the low power design as well as verifications play a major role in the semiconductor industries. So, because so in the emerging eras, the IoT devices, wearable devices, and much more electronics devices coming into market. So each and every customers looking low power consumptions as well as in the design process, the design engineers looking the simulation based verifications along with perfect design. So in simulation based verifications, it is widely used methodology for validating and ensuring the correctness of complex systems, particularly in hardware and software design. This approach involves creating virtual mode of system under test and executing it under various scenarios to observe and analyze behavior and kind expected outcome. The primary goal is to detect and rectify errors and bugs early in the development process, thereby improving the reliability and performance of the final product. So in the power modeling, the context of simulation-based verifications involves predicting and analyzing the power consumptions of the hardware design during its operations. This is crucial in modern digital design, where the power efficiency is a key concern, especially for battery power and high performance devices. So in this, the various key aspects we need to consider, like power estimation, dynamic power analysis, static power analysis, and also one more important thing is thermal impact also we need to consider. So in real-time power monitoring, the various sensors are located in the real-time applications. So the various embedded sensors collecting the real-time power consumption data, then it is transferring to the resources, to the cloud sources or the microprocessor or microprocessing unit. So here the ML algorithms analyze this sensor data to identify power consumption trends and anomalies. So how are we going to close these loops? The closed loop control. The system has the potential to adjust hardware and software parameter to optimize power efficiency dynamically. So in another way, we can say that the runtime reconfigurable device. So here, the, based on the application, based on the various conditions, we may include the device power consumption in the modification. It may vary based on the application, so that based on the input data, based on the scenario where the processing unit going to process the data, we going to change dynamically the architecture so that we can able to reduce the power consumption. Next, please. So various case studies and best practices available in the current scenario. So here we're going to discuss about few case studies and best practices. So in automotive applications, the power optimizations play a major role in the autonomous vehicles and advanced driver assistance system, which is driven by the AI model. Then one more thing is IoT devices. So the ML-based power management for energy constrained Internet of Things devices, looking into the one of the best practices in the reconfigurable architecture. Then final one, cloud computing. So in the cloud computing, we are using various kind of architectures, including virtual machines. So the virtual machine is nothing but we are going to fetch the, or we are going to configure the record hardware configurations in the remote places. The remote places may be who the service going to provide. So in this scenario, the artificial intelligence is used to enhance the efficiency in the cloud infrastructure. So how the artificial intelligence is going to play a major role in this cloud computing part during the configuration of the hardware. So based on the trained data, so here we are going to, as a design engineers, we can able to identify the actual requirement of the hardware. So here the machine learning and artificial intelligence technology is going to support for us to enhance the power consumption. So research opportunities and future trends. Why we are focusing the various kind of future trends and research opportunities. So in the upcoming eras, in the design as well as verifications, the AI and GenAI going to play a major role. So definitely we need to look AI technology in our semiconductor industry. So how is it is going to help in the semiconductor industries? First, so the reinforcement learning. Second one, edge computing. Then neural hardware. So in the reinforcement learning, so it is developing the AI agent that can independently optimize the power consumption in the complex systems. In the complex system, the CAD tool or the design engineer can't able to optimize 100% effectively. So here we are going to apply the AI agent. So it can optimize the power consumption. It's based on the reconfigurable in various levels, which is present in the design flow. So in the design flow, we may start from architecture level and post layout up to GDS. While coming into edge computing, the real-time power deployment of ML models and resource constraints help to reduce the power consumption in various levels. In the hardware part, so it is going to develop hardware that is brain inspired and energy efficient for power sensitivity applications. So in real time, so the customer may use various kind of applications. So in each and every applications, definitely the customer looking low power consumption and high performance. So during the design engineers may consider only high performance or the trade-off between the high performance and power consumption, but definitely can't able to achieve 100% efficiency because we can't able to predict how that design will give 100% efficiency or maximum effective system design. Next, coming into unlocking the power of deep learning in the low power verification as well as in the design part. The importance of low power verification. So as we discussed, so each and every level, each and every customer looking the high performance device along with low power devices. So during verifications, So how the AI play a major role along with the deep learning and machine learning algorithms, which is going to support our low power verification design. So in the energy efficiency, it is essential to optimize the power consumption for mobile, wearable devices, and IoT devices. Coming into thermal management, the reduction of heat generation helps the development of safer and more reliable hardwares. So definitely the thermal management is playing very important role in the chip design as well as PCB packaging. So we can't able to use the chip as a independent. So we need to go for PCB based on the applications. So in the uh, thermal effect will may induce or it will affect the packaging level also. So in this scenario, the various packaging technology also available, even though we need to focus on how to manage the thermal effect during the design as well as verification. Then sustainability, the environmental impact is reduced and ecological initiatives are supported by low power design. So proportionally, it will help the lesser power consumptions. So definitely it will support to environmental impact. Next, coming into leveraging deep learning for low power verification. So various models, analysis, techniques we may focus. So here we categorize a few things. So one is model-based optimization, early stage analysis and runtime monitoring. So in the deep learning model, which can identify the circuit components that consume a significant amount of power and propose them modification to the design. So here we can able to use IP core also during the IC design. So various IP cores are available in the libraries. So as a design engineers, so we can able to find out the suitable IP core based on the customer's requirement as well as the part which is going to utilize, so that the deep learning models definitely going to support to identify the significant or more suitable IP core to pick the IP core for our design, so that it can support to reduce the low power consumption. So in the verification, definitely the verification time going to reduce, because as a CAD tool, as a design engineers, we can't able to find out the exact IP core. So we need to analyze the database. So definitely the deep learning models going to support to reduce the time consumption process as well as the verification durations in the real-time applications. And early stage analysis, the deep learning driven simulations can focus on conceptions at the architecture level. So definitely, so deep learning going to play in architecture level, start from architecture level. So in the runtime monitoring, so how the deep learning will support to monitor the dynamically managing power on deployed hardware is visible through embedded deep learning models. So it's going to play a major role in the upcoming eras. Then coming into research advances in deep learning for low power verifications. So first one, power modeling. Second one, design space exploration. Then runtime adaptations. In the power modeling, as discussed, the deep learning models that accurately predict power consumptions from the circuit, netlist, or RTL level itself. So that the verification time, the number of cycles we are going to iterate the verification process will reduce. So definitely the design may enhance, and also we can able to reduce the power consumption during the verification process. In the design space explorations, the AI guides us to identify most efficient power, low power configurations from enormous design spaces. In runtime adaptations, embedded deep learning agents that purposely adjust power settings in accordance with the workload which is going to adapt. So while coming into real world applications of DL driven low power verifications, the various applications available, the few things are mobile SOC, data centers, then aerospace electronics, then most one is medical devices. The various kind of wearable devices which is going to coming into market in the near future. Definitely each and every things are indirectly going to support the semiconductor industry. So next slide. The future of real driven low power verifications, the automated design, edge AI integrations, and digital twins. In the automated design, artificial intelligence powered devices that generate and optimize low power circuits autonomously. Then in edge AI, directly embedding the deep learning models into the low power hardware to facilitate real time adaptations. Then coming into digital twins, the virtual prototype that utilizes deep learning to forecast verify power behavior. So go ahead, next slide. So research directions and opportunities. So first one is scalable DL models, and second one transfer learnings, and DL based hardware code design. So definitely the hardware code designs in the embedded low power verifications will support the entire semiconductor industry. Next. So coming into conclusions, the empowering low power design with deep learning. So the key advantages are increased energy efficiency, improved thermal management, enhanced sustainability. So how the things are going to include in the real world impact? The first, foremost, mobile devices and wearable devices, data centers, aerospace and medicals. So coming into future outlook, automated design, so AGI, and digital twins. So thank you very much. So I have acknowledged Mr. Mike, the Senior Vice President, VLSI Design TESOL, and Ms. Dizra, the Senior Marketing Executive TESOL, for giving the opportunity to present the webinar. Thank you. Thank you so much.
Okay, thank you very much for the presentation as well. We've run out of time, so we can't ask a question. There is one question. We'll send it on email, and then we'll provide a response directly on email. But thank you for the presentation, Sivanandam and Ramya. Thank you very much. I will share my screen now, so we can quickly wrap up the event. And then we can finish on time. Can you see the screen, please, Disha?
Yeah, Mike, we can see.
Okay, so thank you for participating today. Thank you to our sponsors, Ignisis, Cadence, Brecken, and Synopsys, and for TESOL, who host the event. We will be sharing the PDF of the slides and the recordings. They'll be on that website there, but you don't have to take that down now. We will be sending you an email with the link so you can access the PDF and you can access the recordings. If you've got any ideas for preferred topics for future events, just email me. The event today came out from a suggestion. Somebody emailed in and asked for a presentation on this topic and offered a presentation. So we do listen. If you send it in, the chances are we'll put on an event for that topic. Talking about the events, here you can see other events that are coming up. On the 24th of September, there is an FPGA, it's called FPGA Threat Runners, and it's an FPGA verification strategies. That's on the 24th of September. On the 15th of October in India, it's actually physically in Bangalore, but will be online as well. The FPGA event, by the way, is physically in the UK at Rolls-Royce, but also online. We'll be talking about verification of chiplet-based designs on the 15th of October. And DV Club Europe will be hosting on the 8th of October, Coco TB. And we have an event on the 26th of November. It's just still TBD. Okay, but when we send you the email, we'll be including links to all of these so you can register for these as well. Okay. Again, thank you to our speakers today, who were from India. So the last talk was Ramya and Dr. Sivanandam, and our first speakers today were Satinder Paul Singh, who's actually based in Munich, and Pavan, who is based in India. Thank you very much.
Thank you, sir. Thank you so much.
Thank you, everyone. Thank you for joining.
Thank you all. Thank you very much.